Thank you so much. Thank you. The outset, I wish to thank Professor Panigruhi and the organizers of this event for inviting me and giving me an opportunity to talk to you. I truly appreciate it. Can I share the screen now?
Yeah, please go ahead.
Allowed. Can I start now?
Yeah, please start, Dr. Balakrishnan.
Yeah. Yes. Yeah, okay. So thank you so much. Apologize for the slight delay and inconvenience. So today I'm going to talk on one of the most fundamental and deepest principles of quantum mechanics, which is interference due to path indistinguishability. So how it manifests in quantum mechanics, and I will discuss this in reasonable detail, and after going over the concepts briefly, we will see how it has been realized in an optical platform, as how one can observe interference by erasing the path information. Following this, we will see how this fundamental quantum mechanical principle manifests in a very practical setting, how we can exploit this phenomenon to do quantum imaging and entanglement verification. So that's what I'll be talking about. So I will stop at the end of 15 minutes. So my primary goal is basically to discuss the concept of path indistinguishability in quantum mechanics and how it can be realized, how interference due to path identity can be observed in an optical setting. So the next slide, please. Yeah, the next one. Okay, yeah. So we start with the famous thought experiment that was discussed by Feynman in his celebrated lectures. So this is a thought experiment that has been discussed for more than 70 years. So this thought experiment was first expounded by Niels Bohr in the 30s and 20s, 30s and 40s, and later popularized by Feynman in 60s in his famous lectures. So the thought experiment is the following. This is something that all of you would have seen in his lectures or in one of his YouTube videos. So this is an electron gun. You can see the cursor, right? You can see this little arrow, right? Can you see the arrow? Oh, okay.
No, I don't see arrow.
Oh, no, okay. I'm not sharing this.
Oh, yes, okay. I can see arrow. Yeah.
You can see the arrow, right? Okay.
Yes,
okay.
Yes.
Okay. So you can see me moving this one.
Yes, I can see.
Okay, great. So let us take this electron gun and let us assume that this gun shoots electron one at a time. So if you close slit 2 and just calculate the probability distribution of electrons emerging from slit 1, this is what you would get, the distribution given by P1. Likewise, if you close slit 1 and simply observe the electrons passing through slit 2 and construct its probability distribution, this is what you would get, P2. But if you keep both the slits open, something dramatic happens. You actually see interference patterns. Like there are some spots on the screen where the probability for electron to arrive is 0. And there are some spots on the screen where maximum number of electrons strike it. So, which means the electrons exhibit wave phenomena. So, but the moment you try to observe the path that the electron takes, as say, when you try to observe through which slit the electron passed by, then the interference pattern vanishes. Okay? So until today, we don't know why this is true. There is no deeper principle as yet from which this phenomenon can be deduced. But we know for a fact that this is true. The moment you try to observe the path of an electron or a photon, the interference vanishes. As long as you erase the path information, the interference appears. So this is what Feynman said. We choose to examine a phenomenon which is impossible, absolutely impossible to explain in any classical way, and which has in it the heart of quantum mechanics. And in reality, it contains the only mystery. Okay? So this is one of those deep, mysterious aspects of quantum mechanics, but it has ramifications everywhere. So this interference due to path identity is all pervasive in modern physics. So next slide, please. So yeah, so what it tells us is that if you want to calculate the probability when both the slits are open, you have to first coherently add the amplitude, psi1 and psi2. And when you calculate mod of psi1 plus psi2 squared, you get mod psi1 squared plus mod psi2 squared, and this is the interference term. the psi1 star psi2 plus psi1 psi2 star can be written as 2 psi1 psi2, 2 mod psi1 mod psi2 cos theta. And theta in this particular setting really depends on the location on the screen. And this tells us why the probability amplitudes in quantum mechanics should be complex quantities. So this really tells why complex quantities naturally arise in quantum mechanics. Because if psi is real, then you won't get this interference term. In that case, psi1 plus psi2, the whole square would simply be mod, psi1 squared plus psi2 squared plus 2 psi1 psi2 with no interference term. The fact that you get interference tells us that the probability amplitudes psi should be complex. So the next slide, please. Okay, so before we proceed further, we need to really be careful, like what are the true quantum effects in interference? Because interference is all pervasive in optics. Classical fields interfere, quantum fields interfere. So whenever we talk about interference, we have to be very careful. We need to distinguish classical effects from quantum effects. So almost all interference effects observed measuring intensity are explained by classical theory of electromagnetic fields. And this book by Born and Wolf is one of the best resources to really appreciate classical theory of coherence and classical theory of interference. Okay. Now, these interference effects, which can be explained by classical theory of electromagnetic fields, are not quantum. By quantum interference, we mean those phenomena which can only be explained using the postulates of quantum mechanics. In other words, any attempt to use classical theory to explain that phenomenon should fail. Okay? If only you can explain certain interference phenomena using the postulates of quantum mechanics, can you call that interference effect quantum? Okay. So the next slide, please. Yeah. So the thought experiment that Feynman discussed in 1962 in his lectures was first realized experimentally in an optical setting by Mandel. Mandel was one of the greatest scientists of the 20th century, and he was one of the founding fathers of quantum optics. So he has done some amazing experiments. So this is, I've taken this quote from the tribute paid by Jeff Kimball and Emil Wolf in August 2001, shortly after his death. A central theme of Mandel's research was the exploration of the nature of light through insightful theoretical analysis and a set of pioneering experiments that have become landmarks in the field. Now, this statement is absolutely true. There is not an iota of exaggeration in this statement. So Mandel's experiments were really original and insightful. So he designed an interferometer. He, along with his group members, Zhu, Wang, and Mandel, the three of them, designed an interferometer to realize Feynman's thought experiment in the lab. So this is the first optical realization of single photon interference due to path identity. So instead of superpositions of single or multiple photons, Mandel and his group created superpositions of the origins of a photon pair itself. So when you erase the information about the source that produces a pair of photon, then that's when you genuinely erase the path information. Okay? The moment you erase that path information, you observe single photon interference. The moment you try to retrieve any kind of path information, the interference vanishes. So that's what Mandel and his group demonstrated. So the next slide, please. So we'll just take a small detour to briefly discuss spontaneous parametric down conversion, because this is the process that everybody uses to produce correlated photons. So SPDC, spontaneous parametric down conversion, is abbreviated as SPDC, and this is the workhorse of entangled photon generation in the lab. So what it does is you have a nonlinear medium, which is typically a Chi2 crystal. By Chi2, I mean a second order nonlinear medium. You shine a pump, and the pump photon annihilates inside a medium, and then it creates a twin photon pair. And for historical reasons, we call them Signal and Idler. Okay, and the two conditions that need to be satisfied are conservation of momentum and conservation of energy, which means the sum of the momenta of the Signal and Idler should be equal to the momentum of the pump photon. That is called the phase matching condition. Likewise, the energy of the pump photon, the angular frequency omega sub p, should be equal to omega sub s plus omega sub y. Okay. So these two conditions have to be satisfied in spontaneous parametric down conversion. So in the single mode framework, this is the Hamiltonian. G is it's a parameter that is proportional to the length of the crystal, the nonlinear susceptibility chi2, so on and so forth. And E sub P is the strength of the pump, the electric field of the pump. And AS and AA are the mode operators for signal idler. So initially, we don't have signal idler. So signal idler initially are in vacuum modes, okay? Because you don't have signal and idler until the pump photon gets annihilated inside a medium, okay? The pump annihilates to create a pad, a signal idler pad. So from standard quantum mechanics, the evolved state psi is the evolution operator acting on initial state, and this is the evolution operator. And the pump is weak. We are working at a single photon level. So which means the pump is extremely weak. When we do a perturbative expansion, we can ignore all the higher order terms. We are only going to keep terms that are linear in epsilon. The epsilon is just this coupling strength parameter. I'm clubbing all these parameters into one single parameter for convenience. So G, E sub P, T, time, all these things are clubbed together, and I call that epsilon, okay? So since we are working in a low gain regime, the multiphoton emission is suppressed, and we are going to get only one signal and one idler. So that's why we ignore all the higher order terms. So when you add U on the initial state, this will give you nothing. This is going to give you 0 because the vacuum, the annihilation operator will kill the vacuum modes. And this AS dagger and AI dagger will just give you one signal photon and one idler photon, okay? And these two are correlated. So this is what we call the twin photon state or a biphoton state. These are the jargons used in the literature, okay? So these are, of course, these photons are entangled, but for this experiment, we are not interested in entanglement. The fact that they are correlated is sufficient for us. Okay. Next slide, please. But if you have any question, please feel free to stop me. I'll be happy to take questions in the middle of my talk. So this is the interferometer that was designed by Zhu, Wang, and Mandel. So they took two identical nonlinear crystals, NL1 and NL2. Okay, NL1 is crystal 1, NL2 is crystal 2, and you have a laser, and this is a beam splitter. So the laser is split into the beam from the laser is split into two parts, which is because we want the same identical beam to shine through crystal 1 and crystal 2. We want to ensure that the pump that illuminates crystal 1 and crystal 2 are the same. Is the pump that eliminates crystal 1 and crystal 2 is the same. So each crystal, through spontaneous parametric Down conversion, will produce a pair of correlated photons. So crystal 1 produces its own pair. We call it S1 I1. S1 is signal from crystal 1, and I1 is idler from crystal 1. Likewise, when the pump eliminates crystal 2, it produces its own pair S2 I2. S2 is signal 2 from crystal 2. Idler is I2 is idler from crystal 2. Now, to observe single photon interference, you need to erase the path information, or in other words, you need to erase the information about the source that produces the pair. You should somehow, in your experiment, create a situation where you won't be able to tell whether the pair was emitted by crystal 1 or crystal 2. Now, please note that since the pump is extremely weak, the probability for both the crystals to emit simultaneously is very low. So at any random instant of time, you're more likely to see only one pair of photons, either S1 I1 or S2 I2. But so how do you experimentally erase the path information or the source information? They did something very clever. So they took I1, idler 1 from crystal 1, and aligned with I2 from crystal 2. So basically, they did a mode matching. Okay, so they basically matched the mode of idler 1 with the mode of idler 2. And this little block that you see is basically a filter with variable transmission coefficient T, and this will allow you to control the extent of mode matching. So if T is 0, if T is 0, which means it's going to completely block I1 from aligning with I2, which means you have the complete source information. You know which source produced the photon. If T is 1, then there is perfect alignment, because then you're going to let whole of I1 pass through NL2, and it gets aligned perfectly well with I2, and thereby the which source information is completely erased. So this filter basically, you use this filter as a switch in some sense to really play with the extent of alignment. And this idea was suggested to Mandel and team by Jeff Wu of Hongu Mandel fame. It was his idea to align the idler beams to erase the path information. It was a very clever trick, very original. So then what they do is, once the idlers are aligned, there is no detector here. You don't have to detect the idler photon. But if you were to put a detector here, and if it clicks, you won't know from the detection whether it was due to crystal 2 or crystal 1. Okay, that's how you erase the path information. Whereas if you block idler 1 completely by making T 0, and if you put a detector here and if it clicks, you know that that detection was due to crystal 2. Whereas if there is perfect alignment, if mod T is 1, and you align idler 1 with idler 2, and you put a detector here, the detection will not reveal the source of the idler photon. Okay? And that's what you want. You basically want to erase the source information in order to observe interference. Now, what they did was, then they took the two signal photons, and those beams were combined at this beam splitter, and then they were detected. And they observed interference when the alignment was perfect. So can you go to the next slide, please? Yeah. So basically, when the two crystals NL1 and L2 are eliminated by a mutually coherent pump, you can write down the state. So each state produces its own pair. So, and let us keep things general. Alpha 1, alpha 2 are the coefficients. Okay. Let us assume that, of course, if the pump is perfectly identical in every sense, then alpha 1 will be equal to alpha 2. So the constant will be 1 over root 2. They will carry equal weights, but for the purpose of analysis, we'll keep the weights, the coefficients general. So each crystal produces its own pair. So one signal photon and one idler photon. So basically psi is alpha 1 S1 I1 plus alpha 2 S2 I2. Okay, and the state is normalized. The next slide, please. Yeah. So how is the path information erased? The path information is erased by aligning the idler beam. So you basically, so what does it mean mathematically to align the idler beam? So you're basically doing a mode matching. So this operator AI2 should be some phase. This phase is the phase that idler picks up due to propagation from crystal 1 to crystal 2. It's T times AI1 plus R times the vacuum modes. So T is basically a transmission coefficient that tells you how much of I1 is allowed to pass through crystal 2 and get aligned with I2. Okay, so this T is basically a complex quantity. You can express it as mod T times e to the power I phi sub T. So this is the phase, and this is the idler mode overlap, inner product between I1 and I2. So if that is given by mod T, if mod T is 1, the mode matching is perfect. So that's where you get maximum interference. If mod T is 0, the mode overlap is 0, which means you don't have any kind of path indistinguishability. You have a complete knowledge of the source information, and there won't be any interference. So when you just operate this AI2 on its own vacuum mode, this is what you get. Yeah, please.
What is A0?
So A0 is the vacuum mode because this is we are working on in a quantum optical setting. We need to introduce vacuum modes to the other port of the beam splitter. So you're aligning. So this filter is modeled as a beam splitter with single input. But in order to satisfy the canonical commutation relation, the bosonic mode operators, as you know, should satisfy the canonical commutation relation. So in order to satisfy the relation, the canonical commutation relation, we need to introduce vacuum modes to the other port of the beam splitter. The standard trick that we employ in quantum optics.
Okay, so that is clear, but why did you assume the R?
Oh, R, because the thing is this. So mod T is a measure of how much of idler gets transmitted through the filter. and the remaining portion will be the vacuum modes. So if you just were to calculate the commutation relation between AI2 and AI2 dagger, you would get mod T square plus mod R square, which is 1. Because we are modeling this filter as a beam splitter, a quantum mechanical beam splitter. So whatever portion of the idler doesn't get aligned, the vacuum modes enter through the other port. So so basically it's T AI1 plus 1 minus mod T square A vacuum. The vacuum modes are introduced in order to make sure that the bosonic commutation relationship is satisfied. There is no use for, experimentally, there is no use for the vacuum modes. Does that answer the question?
Yeah, no, it's okay. Yeah, please go ahead. Sure.
Yeah. So the next slide, please. Yeah. So what are the significance of idler beams in the Zhu-Wang-Mandel experiment? So the alignment of the idler beams, basically you're overlapping or making identical the idler photons paths. You're basically ensuring that by aligning I1 with I2, you're forcing crystal 2 to emit I2 in the same mode as I1. That is known as mode matching. You want to make them identical in every sense. Only then will they become truly indistinguishable. So through the alignment of idler photons, the information about the source of the signal photon is erased completely, which in the literature is known as the width source information. So the erasure of width source information induces coherence in the signal photons, as a result of which you observe interference here at the detector D. The extent of the amount of coherence induced in the signal photons actually depends on the quality of alignment. If the idler photons are not properly aligned, that will reflect in the contrast of the interference fringes. This is something that we'll see quantitatively in a few minutes. And if you want to read more about quantum indistinguishability with part identity, this is a good reference. This is a review article published in the Reviews of Modern Physics in 2022. This is from Anton Zeilinger's group, and this is a good resource to appreciate the details of this setup. Yeah, next slide, please. Okay. Now, this is how we define the detection operator. The positive frequency part of the quantized field at the detector D is basically a superposition of S1 and S2. So this is AS1 plus I times e power I phi s AS2. This I phi s is basically the phase difference between the two signal photons, the phase difference that is acquired due to their propagation. So to observe interference, there should be some difference. There should be net difference in the path length, and that path length, the difference in the path length is characterized by this phase phi sub s. Now, from the standard theory of photodetection, using Glauber's formula, if you were to calculate the intensity, which is same as the photon counting rate, that's given by this formula, you get this compact expression: mod alpha 1 square plus mod alpha 2 square plus 2 times mod T alpha 1 alpha 2 and this cost term. Now, look at the interesting thing is the presence of mod T here. If mod T is 0, you see that the interference vanishes. Okay, no matter how you play with the phase, if mod T is 0, the interference vanishes. Okay, and you're likely to get maximum interference when mod T is 1. Okay, and that tells you the presence of mod T in the interference term tells you the importance of alignment. What role the alignment of idler beams the role that the alignment of the idler beams plays in erasing the path information. The next slide, please. Yeah. Now, the visibility is straightforward to calculate. It's given by the standard formula, R max minus R min by R max plus R min. And this is what you get. Please note that the state is normalized. So mod alpha 1 square plus mod alpha 2 square is 1. So it's basically 2 mod alpha 1 mod alpha 2 times mod T. And this mod T is nothing but the idler mode overlap. Now, it really tells you if mod t is 1, and if you assume that mod alpha 1 and mod alpha 2 are equal, say 1 over root 2, then the visibility is maximum. You get the maximum contrast in the interference fringes give you the maximum amount of maximum contrast. On the other hand, if mod t is 0, there is no interference. The interference vanishes completely. So it really tells you how the path indistinguishability directly influences the interference observed on the detector. And if mod t is 0, the interference vanishes completely. The next slide, please. Okay, now we know this is something that we know even from classical optics, that if you want two optical fields to interfere, they should be mutually coherent. They should exhibit mutual coherence. So coherence is basically is the ability to exhibit interference. And if you calculate the normalized mutual coherence between these two signal paths, S1 and S2, the formula is standard. The formula to calculate mutual coherence is the same in both classical and quantum optics. It doesn't change. It's given by this formula, and this gamma 1,2 is basically AS1 dagger AS2, and if you calculate it over the state psi, this is what you get. And gamma 1,1 and gamma 2,2 are basically the intensities of the signal photon produced by crystal 1 and crystal 2 respectively, and you can calculate this normalized in mutual coherence, which is little gamma 1,2, and look at this one. This is a very interesting result. This gamma 1,2 is exactly equal to the idler mode overlap, which is mod t. Okay, so which means this visibility is given by 2 mod alpha 1 mod alpha 2 times mod t, which is same as 2 mod alpha 1 mod alpha 2 gamma 1,2. Now this result, this visibility being proportional to gamma 1,2, there is nothing quantum mechanical about it. This is true even in classical optics. The visibility will depend on the mutual coherence. But what is surprising and what is profound here is that the mutual coherence is exactly equal to the idler mode overlap. Okay? So now you see how the coherence is induced in the signal photon, how the path indistinguishability induces coherence in the signal photon. Okay? So now you see why this is an experimental realization of Feynman-Stott experiment. So what was Feynman-Stott experiment? So Feynman argued that as long as you don't observe the path of the photon or electron, you will observe interference. The moment you try to observe the path, the interference vanishes. So here you see that by aligning I1 with I2 perfectly well, you erase the path information completely, and that's when you get the maximum visibility, the best interference fringes. The moment you try to observe the path by misaligning the idle range completely, by blocking I1 completely, your interference vanishes altogether. Not only does your interference vanish, of course, if interference vanishes, it means the two signal photons no longer are coherent. They are not mutually coherent. That's what it means. Now you can see how the source information directly influences the coherence induced in the signal photons. The next slide, please. Now, this is very important. Can we quantify path indistinguishability? So far, we have been using this term with source information or path indistinguishability qualitatively. But can we be a little more quantitative? Is it possible to relate it to mutual coherence? Because after all, in this experiment, it is the path indistinguishability that induces coherence. So can we find the relationship between mutual coherence and path indistinguishability? It turns out that in Mandel's interferometer, the degree of path indistinguishability, or what you call the intrinsic indistinguishability of the sources, is exactly equal to the degree of mutual coherence. Now, this can be rigorously worked out. I'm skipping the math here due to scarcity of time, but one can follow the analysis that Mandel has developed in this famous optics letters paper and incorporate it into the his idea in the context of the Zhuang-Mandel setup. So in this paper, in the 1991 optics letters paper, Mandel carried out a very general analysis, not particular to this setup, but you can follow that analysis and incorporate that idea here, and you can show that the degree of path indistinguishability, or what you call the intrinsic indistinguishability of the sources, is exactly equal to the normalized mutual coherence, which is nothing but the idler mode overlap, which in this case is given by mod t. So this PID is a real number which varies between 0 and 1. If it is 1, you have perfect path indistinguishability. If it is 0, you have complete knowledge of the source information. And second, an important concept to be appreciated here, though this statement is very crucial to appreciate. An important concept to be appreciated here is that in the Zhuang-Mandel interferometer with single photons, mutual coherence measures the extent of indistinguishability of the two signal photon paths, S1 and S2. This is fundamentally very different from the notion of mutual coherence in classical optics. So please recall that in classical optics, mutual coherence is a measure of how well the two optical fields are correlated in amplitude and phase at different points in space or at different instants of time. Okay, but here, this mutual coherence is basically a measure of how indistinguishable the two alternatives are, the two S1 and S2 are. Okay, so this mutual coherence is basically a measure of path identity between the signal photons. As long as you are unable to track down whether the signal photon that you see at the detector was emitted by crystal 1 or crystal 2, you are guaranteed to observe interference. Okay, so that is why Mandel called this induced coherence. The coherence is induced in the signal photons due to the erasure of path information. Okay, that's why it's called induced coherence. The coherence is induced. So without this path identity, without erasing the path information by aligning the idler beams, S1 and S2 will not be coherent. They will not exhibit interference. The coherence is induced because you erase the source information by aligning I1 and I2. And the extent of alignment is given by this idler mode overlap. So that's why this path indistinguishability is exactly equal to normalized mutual coherence, which is equal to the idler mode overlap. Is this clear? So any question? Because this is conceptually very different from the kind of interference that one investigates routinely. So I just want to spend some time here. So is there any question here? Is there any part that was not clear? So I'll be happy to take questions if you have any on this part of my talk.
Hello, sir.
Yes, please. Go ahead.
Sir, I was unable to understand the difference between the what is?
Do you want me to go to any previous slide?
No, sir. This one only in interference in the classical and the difference between the quantum interference. Can you explain it better?
Yeah. So see, this is not an interference between two different optical fields. What I'm saying is, this is single photon interference. So basically, this is an interference. What you observe in this particular setup, in the Zhuang-Mandel setup, is the interference between the probability amplitudes associated with the two signal paths. So you see, there are two alternatives to produce the signal field, signal photon, right? Crystal 1 can produce one, or crystal 2 can produce one, right? That's what we label them as S1 and S2. And each has its own amplitude. So what you observe is the interference between these two probability amplitudes. So that's what I meant. Now, here you see that this mod gamma 1, 2, this mutual coherence is exactly equal to the degree of path indistinguishability. So what does it tell us? It tells us that this mutual coherence between S1 and S2, between this, is basically a measure of how indistinguishable the two alternatives are. You see, you have two alternatives to produce the signal photon in this setup, either through crystal 1 or through crystal 2. So the mutual coherence tells you how indistinguishable these two alternatives are. As long as you're not able to identify the source that produces the signal photon, you will have maximum coherence induced in the signal field. That is the crux of the experiment here. Okay. So this is not an interference between two different optical fields. This is an interference between two possible alternatives to produce the signal photon. Have I answered your question?
Thank you.
Is this clear? Did I answer your question?
Yes, sir. Thank
Okay.
you.
Okay. So if there are no questions, further questions in this on this part of the talk, so can you please go to the next slide, please? Yeah. Okay. So just to summarize, now you see that since PID is equal to mod gamma 1, 2, this visibility, basically you can replace gamma 1, 2 by PID. So you see that the visibility is directly dependent on the degree of indistinguishability. So if PID is 1, which means you have the maximum amount of path indistinguishability, in other words, you have completely erased the source information, you get the maximum visibility, provided mod alpha 1 and mod alpha 2 are 1 over root 2. And that can be ensured by making sure that the pump that eliminates crystal 1 and crystal 2 is identical in every sense. If PID is 0, if somehow you can figure out the source of the signal photon, if you manage to figure out whether the signal photon was produced by crystal 2 or crystal 1, then PID is 0, in which case the visibility vanishes. The interference vanishes, the pattern vanishes, because the coherence is no longer induced in the signal photon. The coherence disappears, as a result of which the interference vanishes and the visibility becomes 0. So this is the summary of this particular experiment. So next slide, please. Okay, so how much time do I have?
Yeah, you have 12 minutes for the talk and 10 minutes for the discussion.
Sure. So then I will discuss quantum imaging with undetected photons, and if time permits, I will discuss the entanglement verification. Otherwise, we can open the floor for questions after this this particular section. So the next slide, please. So now we have discussed the notion of path identity in quantum mechanics. Now we will see its manifestation in a very practical setting. Now the question is, can we use this very fundamental and deep quantum mechanical principle and put it to some practical use? It turns out that we can. In fact, we can do imaging by exploiting this fundamental quantum mechanical principle. So this is called quantum imaging with undetected photons. And why do we call it quantum imaging with undetected photons? Because in this technique, the light that illuminates the object is not detected. And again, this scheme exploits the absence of which way information or path identity to observe interference. So basically, we're going to use Mandel's interferometer to do imaging. The image is constructed from the single photon interference pattern of light that never interacted with the object. And unlike ghost imaging, where you need to do a coincidence detection to construct the image, here there is no need for any coincidence detection. By simply measuring the interference pattern of the light that never interacted with the object, you can construct the image from the visibility data. And so what is the advantage of, what is one possible advantage of this imaging technique? You can probe the object at wavelengths for which efficient detectors may not be available. Since you're not going to anyway detect the light that illuminates the object, you don't need to care about the wavelength of the field of the photon that illuminates the object. So as long as you have a good efficient detector at the wavelength that you use for detection, you're good. So this technique was invented in Zeilinger's lab way back in 2014. So the next slide, please. Okay, so what are the basic ingredients that that go into quantum imaging with undetected photons? Of course, the basic ingredients are you need two pairs of identically correlated photons. What we have been seeing in Mandel's setup all this while. So you basically need two identical crystals that will produce two identically correlated twin photon pairs. And then, of course, you need to build this interferometer. This is crucial. And typically, imaging is done in two configurations. One is the near field configuration, which is the image plane. And the second one is the far field configuration, which is the Fourier plane. Now, the imaging configurations are not unique to quantum imaging. These are the configurations that are available to you in both classical and quantum imaging. No matter what kind of imaging you do, you can always do imaging in these two configurations. Yeah, the next slide, please. Okay, so first, I would like to discuss quantum imaging with undetected photons in the near field. So this is the setup. So Q1 and Q2 are the two nonlinear crystals. B prime and A are basically imaging systems. They are basically combinations of lenses. If you want to do far field imaging, you will use one lens because, as you know, a convex lens is a Fourier transformer. It transforms the field to the Fourier plane. If you want to do near field imaging, B prime and A will be a pair of lenses. The first lens takes you to the Fourier plane, and the second lens brings you back to the real plane. So for simplicity, I'm not drawing the lenses. I didn't draw the lenses, so we'll just treat the imaging systems by these boxes to avoid confusion. And I1 is, S1 and I1 are the twin photon pairs produced by Q1, and S2 and I2 are the twin photon pairs produced by Q2. So O is the object, okay? And I1 produced by Q1 illuminates the object O, and it's aligned with I2. And once you align I1 and I2, you don't care about the idler photons anymore. The idler photon is undetected. Now, the red lines, which are your signal photons, they pass through this beam splitter and you capture them on the camera. You capture the interference pattern on the camera. So O is the object. Okay. Now, the next slide, please. Now, the theory can be developed rigorously, and if you calculate the photon, the intensity or the photon counting rate on the camera, it's given by this expression. It's integral d rho I. D rho I is basically the object coordinate, the joint probability density of the signal idler photons, and rho sub I and rho sub S are basically the spatial coordinates, times this interference term. Now, why do we call this quantum imaging with undetected photons? Look at this term, the interference term. The left-hand side has the intensity of light that you measured on the camera, the intensity of the signal photon, the red lines, the red beam that never interacted with the object, but it still carries information about the object through this transmission coefficient. So that is why it's called quantum imaging with undetected photons. Even though the red lines, the signal photon, did not interact with the object, they carry information about the object through this interference term. And this P of rho sub I, rho sub S is basically the joint probability density of the signal idler photons in real space. And the fact that this joint probability density in the expression for the photon counting rate tells you that in the near field configuration, the imaging is enabled by the position correlation between the twin photons. So it's the position correlation between the twin photons that enables imaging in this configuration. So which means for this scheme to work, the two photons should be correlated. They should have some kind of certain amount of correlation. If they are totally uncorrelated, you won't be able to do imaging. And you can see this mathematically here, because if the two photons are uncorrelated, the joint probability density can be written as the product of P of rho sub I times P of rho sub S. And you can pull P of rho sub S out of the integral, and you can integrate out the whole thing, and the interference vanishes. The interference term vanishes because it gets integrated out. So for this imaging scheme to work, the photons should be correlated. Stronger the correlation, better will be the imaging and resolution. Weaker the correlation, poorer will be the quality of imaging and resolution. But the fact is, the photons should be correlated in order to do quantum imaging with undetected photons. Okay? If there is no correlation between the two photons, this technique will fail. Yeah, the next slide, please. Okay, so this is a simple simulation. So let us see how the image is constructed for an absorptive object. By absorptive object, I mean that the object does not carry any phase dependence. The transmission coefficient is simply given by mod t, and it can vary between 0 and 1. And for simplicity, let us assume that it's a cardboard cutout, that mod t is 1. So this is the object. We consider the ideal case, no loss of photons. So this is your constructive interference. The darker one is your destructive interference, and you subtract the two, constructive minus destructive, because that's how you calculate visibility. The visibility pattern is Imax minus Imin. Constructive minus destructive, and you reconstruct the image here. Now, when you do the same analysis for a more realistic setting, let us say there are some experimental imperfections like misalignment of idler beams or loss of photons, then you play the same game, whereas you can see from these images that the contrast is reduced. The interference, the contrast of your interference fringes is reduced. But still, you subtract the destructive interference from constructive, and you get the image. Okay. The next slide, please. Okay. So this one, you don't have to. I'm just going to mention this briefly, but you can skip it if you wish, because the image function for an absorptive object is given by this expression. This follows from the theory of imaging. But the crucial thing that I want you to appreciate is look at this expression. The joint probability density for the twin photons generated in SPDC is proportional to this Gaussian factor. Okay, this rho sub c is your camera coordinate, rho sub o is the object coordinate. MS and MI are basically the magnifications of the imaging systems in front of the camera and object respectively. So, but the important thing is, look at this one. L is the crystal length, and lambda s is the wavelength of the signal photon, and lambda I is the wavelength of the idler photon. Now, the presence of this crystal length L tells you that the position correlation, the strength of the position correlation between the twin photons is constrained by the crystal length. Narrower the crystal, stronger will be the position correlations. Why? Because for small l, the spread will be narrower. For if you make the crystal length longer, the spread becomes broader, which means the correlation becomes weaker. If you can go to the next slide, please. Yeah. So here, the minimum resolvable distance, one can calculate this one, is proportional to m sub I times square root of L times lambda s plus lambda I. This m sub I is basically the magnification of the imaging system B. So this m sub I is the magnification of the imaging system placed between crystal 1 and the object. L is the crystal length, and lambda s and lambda I are the wavelengths of signal idler photons. Now you can see that if L is small, D min, the minimum resolvable distance, is smaller. So if you want a better resolution, it's important to use a smaller crystal or a narrower crystal. And second, if you manage to demagnify the beam before it illuminates the object, you are likely to get a better resolution. But experimentally, the catch is the following. the extent to which you demagnify your beam, the idler beam, before eliminating the object, to that extent you have to magnify here. So in other words, the product of the magnifications of B and B prime should be 1. Otherwise, the alignment will become an issue. You want to ensure that I1 and I2 have the same beam waist. Otherwise, you will mess up with the alignment, and that will reflect in the quality of your interference pattern. Interestingly, it turns out that the resolution in the near field configuration depends symmetrically on the wavelength of the twin photons. So that's an interesting consequence. And of course, the image resolution is limited by the position correlation between the twin photons. So it just tells you that the stronger the correlation, better is the resolution. And the correlation is characterized by the crystal length. So for better position correlation between the twin photons, it's advisable to use a narrower crystal, not a thick crystal. You want to use a thin crystal. Yeah, the next slide, please. And again, this is the simulation of 2 points. Basically, these are the camera images. So this is, we have shown the result for 2 cases. One is a weaker position correlation, where we used the crystal length whose length was 5 millimeters, and then a stronger position correlation with 2 millimeter long crystal. Now you can see that when you use a shorter crystal, the points are better resolved. Okay, you can see this clearly from these camera images. You can see the 2 points distinctly here, and when you use a longer crystal or a thicker crystal, it becomes a bit fuzzy. Okay, and we carried out the simulation for the either wavelength was 1550 nanometers, and the signal wavelength, the detected wavelength, was 810 nanometers. Okay? And we set the magnifications to be 1, and the 2 points were separated by 70 micrometers. Yeah. So the next slide, please. Okay. So now briefly, I'll discuss the complementary scenario, like how do you do quantum imaging with undetected photons in a far field configuration. So this is the actual experimental setup. So the presence of convex lenses in each part of the interferometer tells you that you're doing this imaging in the far field configuration, because this convex lens basically takes the field to the Fourier plane. I just wanted to show how the setup actually is, how the setup is built in the lab. So this is a schematic of the setup that was built in the lab. So yeah, the next slide, please. Yeah, again, you basically play the same game, and if you work out the theory, you see that here the photon counting rate depends on the joint probability density in momentum space. Okay, as opposed to the joint probability density in position space in the previous case. Here in this configuration, it's the momentum correlation between the twin photons that enables the imaging. And this is basically the experimental result, a cardboard cutout of a cat. So this is the constructive interference pattern. This is destructive interference pattern. You subtract the 2, you reconstruct the image. So it's a cardboard cutout of the cat. So the transmission coefficient was assumed to be 1. Okay. So this is the result from Zeilinger's lab. And once again, you see that even though you're detecting the signal photon on the camera, it carries information about the object through this transmission coefficient. Even though the idler never, the field that eliminated the object was never detected. Okay, so this is why it is called quantum imaging with undetected photons. Yeah, the next slide. Okay, once again, here you can ignore this one because this is identical to the previous case, except that here the density, the joint probability density is in momentum space. Once again, the joint probability density in the momentum space is proportional to this Gaussian factor, which is the profile of the pump. and this omega sub p is the pump waist. So this tells you that the momentum correlation is constrained by the pump waist. Okay, larger the pump waist, stronger will be your momentum correlation, and smaller the pump waist, weaker will be your momentum correlation. So can you go to the next slide, please? Once again, in this case, the minimum resolvable distance is given by this expression, and once again you can see that it depends inversely on the pump waist. So if you make the pump waist bigger, say let us say it's 180 micrometers, you can clearly identify the 3 slits. But if you make the pump waist small, say 73 micrometers, you see that you can no longer distinguish between the slits, and the whole thing becomes fuzzy. And also, it depends on the wavelength of the probing field. So basically, it depends on the wavelength of light that illuminates the object. So if you try to make the wavelength of the light that illuminates the object smaller, you basically get a better resolution. So here, the wavelength of the idler photon was 780, and here they use 1550, and you can clearly see the difference. A smaller wavelength for the probing field allows you to clearly distinguish the 3 slits. So the next slide, please. And once again, the magnification and the far field configuration is given by the ratio of the wavelengths of the photons. So FC and F sub C and F sub I are basically the focal lengths of the lenses in front of the camera and the object respectively. So the crucial ratio is this one, the ratio of the wavelength of the signal photon to the idler photon. So higher the ratio of signal to idler results in a higher magnification. Again, when the signal photon has a larger wavelength than the idler, you get a better magnification when compared to the opposite case. When you make, if the idler wavelength has, if idler photon has a larger wavelength, then you get a diminished image. Yeah. So the next slide, please. Okay, so what are the advantages and challenges? The advantage of this particular technique is that no detector is needed for the light that illuminates the object. That's one thing. You don't need to do coincidence detection. The second advantage is this technique allows the samples to be probed at wavelengths for which efficient detectors may not be available. Since you're not going to detect the light that illuminates the object, you don't need to care about its detection. So you can probe the sample at any wavelength as long as that particular wavelength doesn't destroy the sample. So as long as that you ensure that one, you have a really you have a lot of flexibility in this technique to probe the wavelength, to probe the sample at wavelengths, even if they cannot be detected efficiently, because they're not going to detect this field anyway. But what are the challenges? The challenges, the primary challenges, you need to, you see, in this technique, the resolution is basically constrained by the correlation between the twin photons in both the near field and far field configuration. So if you want to improve the resolution, we need to engineer newer nonlinear medium that will produce photons with stronger spatial correlations. So that's still a challenge. So people are trying to design new kinds of nonlinear media that will produce photons with stronger spatial correlations. And second, can you perform imaging with a bright quantum source? That's an open question. So I think I'll stop here because I don't think I'll have time to discuss entanglement verification. So maybe the floor can be open for questions.
Okay, thank you, Dr. Balakrishnan, for a very nice talk. Yes, floor is open for discussion. I request questions to be a little brief and yeah, please. Go ahead. Questions?
Yeah, sir, can I have?
Yeah, please. Yeah, I can hear you.
This is Dr. Singh, actually. Just go to the previous slide, sir. You mentioned about the image there.
Yeah, the previous slide.
Yeah, this one. Yeah, the lambda value you put the lambda in one is 1550, another is 780, right?
Yeah,
The
yeah,
next
yeah,
is
yeah, yeah.
the lower one, and the next you see there's 810 nm and 840 is higher. Can you explain how this happened actually? What is the logic behind it?
Oh no, okay. So this experiment was performed using two different sources. So for one kind of crystal that was used to produce correlated photons, the signal was at 810 and idler at 1550. Okay, and then they used a different source. A different crystal was used, and the experiment was repeated. So for the second crystal, for the second trial, a new crystal was used, and that produced signal at 842 and idler at 780.
Okay. Means the here that object is same, right?
Object is same, the setup is the same, but you see, so once you choose the wavelength of the pump and the crystal, the wavelengths of the signal idler are fixed. They're determined by the phase matching foundation. So you don't have control over that. So the phase matching condition will determine the wavelengths at which the twin photons are produced. So for one particular kind of crystal, the signal was emitted at 810 and idler at 1550. For another crystal, signal at 842 and idler at 780. So basically, so these two results that you see, the diminished image and the magnified image, they are the results from two different experiments using two different kinds of sources. That was done to ensure to explicitly demonstrate this result. The fact that the magnification result depends on the ratio of the wavelength of signal to idler, and the higher ratio of the wavelength of signal to idler results in a higher magnification. To demonstrate this result, they used two different sources to produce twin photons at different wavelengths.
Lambda stands for?
Wavelength. So lambda is the symbol for wavelength.
S, lambda S, what does it mean?
So lambda sub S is the wavelength of the signal photon. The signal is the field photon that is detected by the camera, and idler is the photon that illuminates the object but not detected. So I stands for idler, S stands for signal.
Okay, thank you, sir. Thank you very much.
Okay, thank you.
Thank you.
Yeah, thank you.
Okay, any other question?
I have a question.
Yeah, brief question.
Yeah, please. Yeah.
So thank you for a very interesting and informative talk. So in last part of your talk, you mentioned about quantum imaging by considering bright photons. Question regarding quantum is still open. So could you explain briefly reason behind it?
Oh, okay. So you mean why it is still open? Is that a question?
Yes.
Why?
Yes.
Okay. So the thing is the following. In this case, in Mandel's setup, the setup that was used, you see, the pump is extremely weak. We are working at the single photon level. So which means there is no stimulated emission. The multi-photon emissions are suppressed. That is why this phenomenon is called induced coherence without induced emission. Without induced emission means no stimulated emission. Okay. Now, the moment you use a bright source, it means you're going to make your pump stronger. Okay. So which means there will be multi-photon emissions. So you'll no longer be working at the single photon level. So crystal 1 and crystal 2 will no longer produce a pair of correlated photons. You will have 1 photon state, 2 photon states, 3 photon states. So multi-photon emissions cannot be ignored. That's the first challenge. So which means it requires a different kind of theory. That's the first thing. And second, when you have multi-photon emission, then you will end up seeding crystal 2 strongly. In that case, what will happen is the intensity of signal 1 and signal 2 will be different. Now, you know that in an interferometer, when you have the two arms of interferometer have different intensities, then the visibility gets degraded. So, and you are doing imaging, the image is constructed from the visibility pattern to begin with. So you want to make sure that the intensities in the two arms of the interferometer have comparable photon numbers, mean photon numbers. That's one thing. Of course, that problem can be tackled all you can do is you can put an attenuator on the path of the signal arm that has a higher intensity and try to make the intensities comparable. But the question is, when you throw away photons, are you also losing information? Will you be destroying the coherence induced in the field? That's one thing to look into. Second is, how bright can you make this source? The reason is, if you make the source too bright, if you keep cranking up the intensity of the pump, then at some point of time, you will reach the classical regime. The states that are produced by the crystals may no longer be quantum states of light, they would be classically correlated fields. So when you do imaging with a bright quantum source, one has to first make sure that the source is quantum. You need to test and characterize the source and make sure that you're still in the quantum landscape, and then do imaging, because one cannot arbitrarily increase the strength of the pump just to make the source bright, because if you do that, at some point you will end up reaching the classical regime.
Thank you.
Yeah, does that answer your question? Have I answered your question?
Yes, thank you.
Can you share this slide, please?
Yeah, I already shared. Yeah, I've shared the slides with the organizers already.
Yeah, okay. Thank you.
Yeah.
Any other questions? Okay, if not, then let's thank Dr. Balakrishnan again for a very nice discussion and very nice talk.
Thank you.
Thank you. Thank you. I hand over the session to the organizers now.
Good evening, everyone. Thank you, sir.
Thank you, sir.
On behalf of our organizing committee, I would like to thank Chairperson and Speaker for giving such a nice talk and for contributing to the activity. Thank you, Chairperson, for giving your valuable time.
Sure.
Thank you, everyone.
My pleasure. Okay. My pleasure. Okay.
So we conclude the session today. Tomorrow at 10 o'clock, we'll start again. So this is for today. Thank you. Thank you, everyone.
Thank you.
Yeah,
Professor Balakrishnan, I have one more question. So
sure, please,
allow me to ask. I
sure,
think
please.
In the first part of your presentation, non-quantum imaging section, I mean, if you bring in your calculations wave packet, I mean localization of the photon in the space, then in this case, what kind of changes you may expect?
Well, okay. So, in fact, the question that you asked is similar to what we did in quantum imaging, because the moment you treat the photons as wave packets, you're basically bringing into account the multimode nature of the field.
You're localizing also the photon, and you are not, I mean, using plane wave mechanism in this case.
No. In imaging, we basically we expand the field in plane wave modes, because so when we do quantum imaging, one thing is you only consider the propagating part of the field.
Yes.
Basically, that's why the quantized field operators go as the mode operator times e power ikz. They are propagating modes. You don't take the evanescent modes, anything into account. So
one more question.
Yeah. Please go ahead. Yeah. No, was there a question?
Sir, in these 4 experiment, there is a detector in and we observe the pattern of interference.
Wait a minute, Anika. There's already discussion going on. Can you please hold on to your question, please?
No
Dr. Balakrishnan is already answering your question.
What? Okay.
Your comment is related to that question? Are you commenting and related to that question, Anika? Okay, Dr. Balakrishnan, please continue your explanation.
Yeah. To answer Dr. Ranjit Singh's question, so this will hold good even if you treat the field in the multimode framework. So you can treat this field in multimode framework, and that analysis is not going to be very different from what we do for imaging, because the alignment, everything is the same, except for the fact that your field operators, the alignment condition, everything will have to be written in the multimode framework. So even this, so the fact that if you recall in the expression that I had for photon counting rate when I discussed imaging, it was in the multimode framework, and you did see the presence of the transmission coefficient or basically the idler mode alignment in the interference term.
Yeah, but allow me to explain more in more detail. When you are considering wave packet, and when these wave packets are, propagating in the space, then you may see effects like diffraction and effects like spreading of your wave function. So here, I was just trying to find out whether you will see the same effects which you have discussed, or will you see some changes, and what kind of changes you may see here.
Yeah, so diffraction certainly you will see. So this technique does not beat diffraction. There is diffraction, so the resolution is limited by diffraction, because we are only, when we do imaging, we only consider the propagating field. The evanescent field is not considered. So as long as one doesn't consider the evanescent field, we cannot beat diffraction. So you're right in saying that the diffraction effect will show up, and it does show up. Now, as far as propagation is concerned, we are basically doing the imaging on the source plane. So when you do imaging, you can always assume that the source is at z equals 0, and you're going to image on that plane. So the propagation doesn't play a role in imaging. But propagation will play a role if you were to consider a different problem. If you really want to study how the correlations weaken, or how they vary due to propagation of wave packets, then you're right. You will have to explicitly consider how the entanglement changes, how the correlations decay with distance and time. But for imaging, we are not considering propagation. There is no propagation. That's why you didn't see any z dependence in the analysis. So I'm assuming, I can legitimately assume that I put my source at z equals 0 plane, and I'm just imaging that plane on the camera.